Okay, in this problem, they tell us that a 50-gram sample of a metal heated to 120 degrees is placed in 100 milliliters of water at 25 degrees Celsius. Once thermal equilibrium is achieved, the final temperature of the combination is 30 degrees Celsius. They give us some useful information, including the heat capacity of the water and the density of the water. They'd like us to determine the heat capacity of the metal, and we're supposed to assume that no heat is lost to the surrounding container or the environment. All right, so how do we analyze this problem? It looks like we have a hot object, the metal, coming into contact with a cold object, the water, and there's no reaction occurring. So in that case, we start with just a transfer of energy, our first law of thermodynamics that says heat lost is equal and opposite in sign to the heat gained. Heat lost by the hot object. I'm going to go ahead and start that out by writing Q lost, and in this case, it's lost by the metal, equals negative Q that's gained, and in this case, the thing that's gaining heat is the water. Okay, now we just need to decide how is that metal losing heat and how is that water gaining heat? Our metal. The metal starts out at 120 degrees. It ends at 30. It's not going to melt and become liquid. It's not going to vaporize. There's no phase change. All it does is cool down. So heat for temperature changes, we calculate that by using MCAT. This is going to be mass of the metal, specific heat of the metal, temperature change of the metal sample. That equals negative. Now what's our water doing? All our water does is go from 25 degrees to 30. No phase change occurs. It's just a temperature change. So the way we calculate heat for a temperature change, again, is MCAT. We're going to have MC delta T, but this time we're talking about the water. We know the temperature change of the water, the specific heat. What we really need, though, is the mass of the water. We don't have the mass of the water. All we have is the volume, 100 mils. But they gave us a density. We can easily change 100 mils into grams using the density. It's a gram for every mil. So if we have 100 mils, we have 100 grams. You can also use the density as mass time over volume formula, or we could just do a little conversion here. We could say we have 100 milliliters of water, and it's 1 gram for every 1 mil, so it's 100 grams. Okay, let's go ahead and plug in our data. We have the mass of the metal over here. The mass of the metal was 50 grams, 50.0. I'm looking for the specific heat of the metal. That's the variable that I want. So this we're just going to leave as C. Now, temperature change of the metal. Your temperature change is always final minus initial, and it's really important to keep track of your positive and negative signs. So our final temperature was 30 degrees Celsius minus the initial temperature that we had. That was 120 degrees Celsius. That equals negative. Mass of our water, we already established that that was going to be 100 grams. The specific heat of water, well, that's our 4.184 joules per gram degrees C, and temperature change of the water, final minus initial. The final is 30.0 minus the initial temperature was the 25.0 degrees Celsius. Okay, so what we have right now is 50, our mass, times our variable, which is the specific heat capacity, times the temperature change of the metal, 30 minus 120, well, that's negative 90 degrees Celsius. If you forget about that negative sign, this equation will not work out. The temperature lowered in that case. This equals negative 100.0 times 4.184 times your temperature change here, the water went from 25 to 30. That's a positive 5 degree temperature change. And now we need to just simplify. 50 times negative 90 is negative 4,500 times our variable, the specific heat capacity of the metal. That equals a negative 100 times 4.184 times 5 is a negative 2092. Now, your negative signs are going to cancel out. Very important. The negative signs have to cancel out because we cannot have negative heat capacities. They don't exist. So if we go ahead, in order to solve for the heat capacity, divide both sides by 4,500, you get a specific heat capacity of this metal of 0.46, and that's going to be in joules per gram degree C, and that is very typical of metals. Metals have specific heat capacities somewhere under 1, between 0.2 and 1 in that range. So I hope that helps. Take care.